We are learning how to find electric field due to different charged objects. In this lecture, we will see how to find electric field on the axis of uniformly charged ring. Uniformly means charge is equally distributed all over the objects. First, we will see a short recap of what we have done in previous lectures. We have done how to find electric field due to uniformly charged arc. In order to find the electric field, we have chosen a small differential element of length dl, and due to this differential element, electric field will be in this direction and it has two components dex and dy. The dy vector get cancelled out as due to symmetry, and dex vector get added up, and we end up with the equation which is equal to ex is equal to 2k lambda by r into sine alpha by 2. The electric field will be in this direction only, or the direction which is parallel to the angular bisector. One more thing we have done, which is electric field due to uniformly charged straight wire. Same thing have done in this also. Likewise, our previous derivation, in this derivation we have chosen a small element and find electric field to this element, and taking cos theta of this d vector, we will get d perpendicular, and sin theta of this d vector we will get d parallel, and end up with two equations which is e perpendicular and e parallel. First, we'll deal with basic maths and tools used inside the lecture. First of all, the Pythagoras theorem, which is equal to h square is equal to p square plus b square. Then a trigonometric ratio of cos theta, that is equal to base by height, an exponent a to the power m into a to the power n is equal to a to the power m plus n. Electric field due to a point charge given by kq by r square. We have also done these things in our previous lecture. Only because you don't have a slight of doubt due to mathematics in physics. We have given a uniformly charged ring of radius r having net charge q on it. Let us suppose a small differential element having charge dq on it. We will try to find electric field due to this dq element at this point and integrate for the whole. This dq element makes an angle theta with this axis passing through the center of this ring. Now electric field will be in this direction. Likewise, our previous lectures, it has also two components. One is dex and another one is dy. But dy get cancelled out, as we have seen in our arc. Whenever there is symmetry, the dy get cancelled out, and dex get added up. So there is only field in the direction of dex, or the axis passing through the center. Now you can write d square is equal to x square plus r square in this triangle, and also cos theta is equal to x by d, or cos theta is equal to x by x square plus r square to the power 1 by 2, or root under x square plus r square. Now the magnitude of this vector dE vector will be k dq by r square, since dq is the charge on this small element and t is the distance between this point to this point. Now we put the value of d square from here to here. For dx vector, we have to take cos theta of this dE vector. Now we put the value of cos theta from here to here. The power of x square plus r square get added up, as we have studied in our basic maths, that whenever exponent a to the power m into a to the power n, we can write this equal to a to the power m plus n. So the power of here x square plus r square is 1 and here is 1 by 2. So this get added up and become x square plus r square to the power 3 by 2. Here k is constant, x is also constant. X is not changing, x is fixed. In question, it is given that you have to find electric field on the axis from the x distance from this center. So x is fixed here, and integral dq will be equal to net charge on this ring, which is already given here, which is equal to q. So we end up with this equation. Electric field Ex is equal to kqx by x square plus r square to the power 3 by 2 in the direction of x-axis or axis passing through the center. Field is only along the axis passing through the center. There is no field in the y-axis. One more thing is here. Suppose when x tends to 0 or x is equal to 0, we are here and we know the electric field at the center of the circle or ring will be equal to 0. We have seen this thing in our previous lecture when we have studied related questions of arc. As we move away from this center, electric field increases and then decreases. So there is the maxima here, which is equal to r by root 2. On differentiating this equation with respect to x, we will get two values of x plus minus r by root 2. So field is maximum at r by root 2. On differentiating E with respect to x and equating it to 0, we can easily find the value of this maxima. Likewise, same curve below the x-axis in minus x direction and maxima at x is equal to minus r by root 2. We can see also here, suppose this is our curve. The same curve will be in the negative x direction, and here also maxima will be minus r by root 2, and here maxima is r by root 2. So if we move away from the center, then graph for this will be like this, and if we move in minus x direction, the electric field will change like this. One more thing is here, if identical charges are placed on the vertices of n side of regular polygon, then the electric field on the axis of polygon perpendicular to its plane passing through the center is maximum at a distance of a by root 2 from the center, where a is the distance of each charge from the center. Suppose instead of this ring we have a regular polygon here, then electric field will be maximum at r by root 2 from the center. No matter whatever the shape of this thing, either it is a ring or a regular polygon, the electric field will be maximum at r by root 2, where r is the distance from each charge. Suppose here is a hexagon or a pentagon, regular pentagon or regular hexagon, and if the distance from each charge is r or a, then the electric field will be maximum on the axis at a by root 2 or r by root 2 from the center. We'll do more question based on this note in our tutorial lecture. Here is the related question. First try to read the question. Positive charge q is distributed uniformly over a circular ring of radius r. A point particle having a mass and negative charge minus q is placed on its axis at a distance, we have forgotten here to write x distance from the center. Find the force on the particle assuming x is less than r. Find the time period of oscillation of the particle if it is read from there. So if we try to draw the statement, then it will look like this thing. This is our circle or circular ring of radius r, and x distance from the center, there is a negative charge here having mass m, and force due to this negative charge will be in this direction, as this is of q charge. So electric field will be in this direction and force will be in this direction, and we know the electric field due to a ring on the axis will be given by kqx by x square plus r square to the power 3 by 2. So you can write force is equal to q into e towards the center. Now we simply put the value of e from here to here, on applying approximation, which is r is greater than x, then we can write x square plus r square is equal to r square. So the force will be kqx by rq. This will become r square and r square to the power 3 by 2, which is equal to rq. So our force will be kqx by kqx small q by rq. Since F is a restoring force, since F is directly proportional to x, therefore motion of charge will be SHM. Here F is directly proportional to x, the motion of charge will be SHM, and time period of SHM will be given by 2 pi root under m by k. This k and this k is different, so I have written here k dash. Just simply put the value of k from this equation, which is equal to kq by rq, and find the value of time period, which is equal to this. Thank you.